Hello and welcome back to the video series on linear algebra. So today we will be starting a new topic, and topic is going to be called bases. So the first thing we will be looking at is what spanning is. Spanning. Now we have a definition. So definition. Let V be a vector space as usual over a field F, okay, and we let x1 up to xn be elements of V. Okay, so they're vectors in V. Firstly, okay, we say an element x, which is in V, we say is called a linear combination of x1 up to xn. Okay, so it's called a linear combination of x1 up to xn if there are a set of elements a1 up to an which are in the field F, such that x is equal to a1 times x1 plus an xn. Okay, so what this means is if I have my vector space V here, this is my vector space V, and I pick an element, so I take x in V. Here are elements x1, so this is x, this might be x1, this might be x2, this might be x3, this might be x4, and if I have my field here, which has elements a1, it has an a2 in it, it has an a3, I say that this vector x here, so if I take this out, this vector here is called a linear combination if I can find a corresponding set of a's and a set of x1, x2, x3, such that when I add them all up, I get x. Okay, so that's what this means. Okay, so if I can find a set of a's and I can find a set of other x's in my vector space, add them all up, and I can get x, then we say it's called the linear combination of the other set of vectors. Okay. Secondly, we say the subset of V consisting of all linear combinations of x1 up to xn is called the span of x1 up to xn. Okay, so the subset of all linear combinations is called the span. Okay, that's what the span is of x1 up to xn. Okay, and we denote the span as the span of x1 up to xn. Okay, that's what the span is denoted as. Span, or sometimes we might use span just to show us over this field. Span f of x1 up to xn. Oops. Okay, but that's what we use to denote the span. Okay, and in set theory terms or other notation, the span of x1 up to xn is the set a1 x1 plus ... plus an xn, such that a1 up to an are elements of our field, okay? So that's what the span is, okay, of an arbitrary set of vectors. And finally, we say that x1 up to xn spans our vector space V, so it spans V, or x1 up to xn form a spanning set of V, if V is equal to the span of x1 up to xn, okay? So this means you choose any x in V. So here's V. If I pick which has a set of vectors in it, and here's our field F, this is very unconventional notation. I'm just doing it intuitively so I can demonstrate to you, but this is not what you're going to see in any textbooks or anything. But if I choose any x in here, so I randomly choose any x in here, then this x is a linear combination of all the other x's over the field F, okay? That's for any x, okay? Any arbitrary x. Okay, so if we look at a small example, so if we take V to be the set of all matrices of 2x2 matrices with real entries, and we take F to be the field, which is just the real numbers, then these vectors, or matrices here, A1, A2, A3, A4, where this is A1, this is A2, this is A3, A4, span V. Because I can take any matrix I want, so let me give you a quick example, and you can see for this for yourself. I can take any matrix I want, so for instance 5, 2, 1, 3, and I can say this is equal to 5, 0, 0, 0, plus 0, 2, 0, 0, plus 0, 0, 1, 0, plus 0, 0, 0, 3, which is then equal to 5 times A1. I really should be underlining these because these are vectors, but you get the message. 2 times A2 plus A3 plus 3 times A4. Okay, so these set of vectors span V, okay? And so there are a linear combination, okay? So the span is the linear, so any vector is a linear combination of A1 up to A4. And do remember, in this definition, it doesn't limit the amount of vectors we could have. So if I take A1 up to A4, and then I take another vector, A5, okay? V is also equal to the span of A1, A2, A3, A4, A5, okay? However, A1 up to A4 is a minimal spanning set, okay? But it doesn't mean it's the only spanning set. There are an infinite possibility of spanning sets. So I could take A1 equal to a half as the first entry, 1, 1. Or I could take A4 equal to 0, 0, 0, 5. There are an infinite amount of sets, okay? So we'll go down to a question. So my question to you is the following. Does the set of vectors 1, I, and 2, which are in the vector space C2, which is the set of column vectors with dimension 2, we'll look at what dimension is further on, over the complex numbers, do they span C? So did a span C, so I encourage you to pause the video now, have a go, see if you can come up with an algebraic proof, and we're going to go over the